Okay, these are the 4.4 notes. We're going to talk about conditional probabilities from a two-way table. We're going to talk about conditional probabilities like from a formula, how to use a formula for it. And then we're going to define what does it mean if two events are independent of each other. Okay, so a little bit of review here. We had gender and whether they had their ear pierced or not, okay, and how many people were in that. So a little bit of review. Okay, try and do these four problems. Pause the video and try and do them yourself. Okay, probability that somebody is male. Okay, out of the sample space of 178 people, we had our males were 90 of them. Probability of somebody has an ear pierced. Ear pierced, yes, was 103 out of the 178 people. Okay. Remember, this is an AND statement. Okay, so male and, it's the intersection, male and pierced. So male and pierced was 19 out of the 178 people. And this is an OR statement. Okay, male or pierced. So males were 90 people. And pierced were 103 people. But we counted these 19 people twice, right? They were counted as males and they were counted as pierced. So I want to subtract those 19 people away. Okay, so let me get my calculator. 90 plus 103 minus 19 gives us 174 people out of the 178 people. Okay, another way to think about that was you could add this plus this together. Okay, those are all those categories there. Okay, now the new idea for us is an idea of conditional probability. We're given something. Okay, so for example, I would have everyone in the class. So if I would ask everyone in the class, what's the probability somebody's wearing red? Okay, so I would take all, let's say there's 20 people in our classroom, and I'd ask all the people wearing red to stand up. Okay, and let's say there were 7 of them. Okay, now the next question I would do is, what's the probability of somebody wearing red given that they are a female? Okay, so this little line here means given that they're a female. Okay, so now with the given idea, we're no longer looking at everybody in the classroom. We're given that they're females. So what I would ask just the females to stand. Let's say there's 12 females in the class. So we're just looking at the 12 females. And then out of those 12 females, how many are wearing red? And let's say there were 5 of them. Okay? So that's how I would introduce it in the classroom. So when something is given to you, you're no longer looking at the whole population. You're only looking at a certain group of people. Okay? And then taking the probability out of that group. So if we go to this problem. Okay, so male given that they're pierced. So we would write this as probability of male given that they are pierced. Okay, so now we're given that somebody is pierced. So we're not looking at the whole population. We're only looking at whether they had pierced ears. Okay, so we're looking at this group of people, the 103 people. And then out of those 103, how many of them were males? That was 19 out of the 103. Okay, okay, pause this one and try and do this one yourself. We went pierced given that they are male. Okay, so given that they're male, so we're only looking at the males. Okay, there's 90 males here in this category. Okay, 90 males. And how many of them were pierced? We had 19 out of 90. Okay, so that's the whole idea of given. Okay, that's with a conditional probability. Okay, so let's look at this example here. They took a random sample at Yellowstone National Park. By the way, they have snow there right now. Of 1,526 visitors during winter. They asked each person whether he or she owned, rented, or never used a snowmobile. And the respondents were then asked whether they belong into an environmental club, like Sierra Club or something. The two-way table describes their responses here. Okay, so part A, find the probability of N never used given that they are in an environmental club. Okay, so E is environmental club, S is snow owner, N is never used. Okay, so so we're given we want to look at the given that they are part of an environmental club, okay? Because it's given that they're an environmental club. So an environmental club given, yes they are. We're looking at these 305 people. Okay, so my sample space is the 305 people. Now out of those 305 people, how many have never used? 212. So our probability for that would be 212 out of 305. Okay, part B says given that the person is not a snowmobile owner, okay, so not an owner, what's the probability he or she is in an environmental club? Okay, so writing it as we want the probability that they're in an environmental club given that they are not an owner. Okay, so we're not looking at everybody, we're just looking at non-owners. So not an owner, okay, so these people are owners, so these people are not owners. Okay, so renter or never used, we got to combine those two groups together. Okay, so we have to take that 657 and add it to the 574. Okay, or I could have taken that minus this, right? So people that have not owning are 1231. Okay, so the people that have not owned is 1231. Now, out of these 1231 who do not own, how many are in an environmental club? So that would be this category, these right here. So 1, 2, 12, and 77 together gives you 289. So out of those that do not own a snowmobile, we have 289 of them in an environmental club. Okay. Okay, basically, if you want to use a formula for this, okay, for conditional probability, so that we can use, say, the probability of B given that A happens, okay, is the probability of B and A happening divided by just the probability of A. Okay, so that's kind of our general formula that we can use for these conditional statements. Now if it's in a two-way table, think through what we just thought through, right? So male given pure steer, so given the pure steers was yes 103, males were 19 out of the 103. Okay, this kind of gives you an idea, you know, how it goes through it, but that's the basic formula. So if we use that formula, let's use it right here in this problem. Classify the residents in a large complex. Either they read USA Today or they read the New York Times. There's our Venn diagram. What is the probability that a randomly selected resident who reads USA Today, so we're given that they read USA Today, which is 40% of the people, right? They also read the New York Times. So out of this group, how many read the New York Times? 5%. So we're looking at our 5%, those that read the Times, out of the 40% total of A. Okay. Okay, the next thing is talking about independence. Okay, so are two events independent? Okay, so now I'll give you some examples. Let's say I have two events. One event is flipping a coin, and the other event is rolling a die. When I flip this coin, I'm going to get either heads or tails. Does the outcome of this affect what happens to this next one? No. Okay, so we would say these two events are independent of each other. Okay, so if yes, so if they are independent, then one event does not affect the other. Okay, so just because I flip this, whether it's heads or tails doesn't really impact whether it's still going to be a probability of 1/6 for every one of these numbers, right? Okay, now I'll give you an example of not independent. Okay, so let's say we take these cards here. Okay, if I take these cards, so we'll just take let's take red. Okay? The probability of getting a red card, I mix them all up here, right? Probability of getting a red card is 1/2. You know, half of them are black and half of them are red, right? Okay? Now, if my first event is a red card and my second event is a red card, okay? So the probability of getting a red card, there's 26 reds out of 52 cards, okay? So let's say I picked a card. That's, I could use black, I'm just going to say it's a red though, okay? I pick a card and it's a red card. Okay, now, since this event already happened and I'm leaving this card out, what's the probability my next card's going to be red? Okay, well, there's only 25 red cards left and there's only 51 cards left altogether. So this next event is not independent of this first event because it changes, okay? So if they're not independent, then one event affects the probability of the other. Okay, so that's the whole idea of independent. Okay? So when we put it with conditional probability, it's basically this. If I have the probability of A happen giving that B happens, right? If they're independent of each other, B should not have an impact on A, right? If they're independent, B doesn't have any, okay? So if they're independent, I know that the probability of A given B happens is going to be the same thing as probability of A if they're independent, okay? If they're not equal to each other, then I know they're not independent, okay? That B did have an impact on A, okay? So let's think about this here, okay? We'll go to this male, female, pierced ear, not pierced ear. Okay, let's have the idea of pierced and male. Okay, so are pierced and male independent? Okay, that's my question. Are they independent events? Okay, so we have to find the probability of pierced given that somebody is a male. Okay, and that should be the same as pierced given, probability of just pierced, right? So if being a male has an impact on the probability of being pierced or not, we're going to find out, okay? So pierced given male, okay, so males were 90, and there were 19 out of 90 which were pierced. And then just overall, the probability that somebody was pierced was 103 out of 178, okay? Now, if these are independent events, these should both equal the same thing. 19 out of 90 gives me 0.21, and 103 divided by 178 gives me 0.58. Okay? So since these are not equal to each other, pierced and male are not independent. Okay? If I know that somebody is a male, the probability that they have a piercing is less than the general population. Okay? So the gender has an impact on whether I know that the probability that somebody is going to be pierced. Okay? Okay, let's do a different problem. Okay? Is there a gender and handedness? Okay, so male and female, and whether they're right-handed or left-handed. Okay, they took 100 students in Australia and they completed a survey, and these are the results. We want to know, are the events male and left-handed independent? Okay. So we got to find two probabilities. We got to find the probability of male given that they're left-handed, and if they are independent, it should equal the same as probability of just getting a male. Okay, so let's find male given left-handed. So given they're left-handed, would be 10 people are left-handed, and males are 7 out of those 10. So that's 0.7. Probability that somebody's male was 46 out of 100 people, which is 0.46. Therefore, those two events or categories are not independent. Okay, knowing that somebody's left-handed, there's more males than that, right? So that changes the probability of it. Okay. So let's think about this one here. Is there a connection between independence of an event and whether there's an association? Yes, there is. Okay, thinking back to chapter, what was that, 2.1.2 or something like that. We looked at this and we thought about is there an association between these? Okay, so remember there was an association if there was a difference between them, right? If there's no association, they're the same. So here there is an association. More males were left-handed than females, right? Less males were right-handed than females. Okay, so there is an association between those. It also tells us that since they're not the same, they're also not independent of each other. Okay, knowing their gender will help us predict whether they're right-handed or left-handed. If I know they're male, they have a higher percentage of people left-handed than right-handed, right? Okay. Okay, one last problem for us. Students at the University of New Hampshire received 10,000 course grades in a recent semester. The following two-way table breaks down these grades by school of the university taught. The schools of liberal arts, engineering, and physical science, and then health and human services. Okay, so there's 3 schools within New Hampshire, University of New Hampshire, and then A, B, or something lower than a B. Okay, so part number 1, E it comes from an EPS course. L means that it's lower than a B. Okay, so probability of L that it's lower than a B, given that they were in this course. Okay, so we're given that they are in this course. So in this course, there's a total of, we got to add all these together here. How many people are there total in one of these courses? 800 plus 432 plus 368. Okay, so in these courses, there were 1,600 students. Okay. Now, how many of those students had lower than a B? Okay, 800. So almost half of them, right, 50% of them had lower than a B. Okay, so part B, are L and E independent? Okay, well, I know that L given E should be the same as probability of just getting lower, right? So if they're independent, it shouldn't matter what they're in. It should be overall. We should have 50% of them, right? So L given E was 50%. We just found that. Probability that somebody got lower than a B, let's figure that out. So lower than a B were this group plus this group plus this group. So if I add these together here, there were 2952 out of the total of 10,000 courses. And that gives us 0.2952. Okay. Now, what does that tell us? That tells us that overall, out of everybody, about 30% of the people got lower than a B. Okay, in all the courses, about 30% of them got lower than a B. But there was a higher percentage of them in just this engineering and physical sciences. We had almost half of them get lower than a B. Well, we did have half of them get lower than a B. Okay, so they're not independent of each other. Knowing that they're in this group of classes tells us that there is a higher percentage of them getting lower than a B than the general population. So they are not independent. Okay, so we did a couple things. We found and interpret probabilities using the conditional probabilities given something using the two-way table. We used the probability formula. Okay, remember that formula, B and A divided by A. And whether two events are independent. Independent means does one affect the other? Okay, does knowing one thing about something affect the other? Okay, come ready to class with some questions.